Hello everybody, we're going to talk today about force basics. Specifically, we're going to talk about the types of forces, we're going to talk about free body diagrams, and we're going to talk about mass and weight. Alright, so let's get going. Now, basic definition. Force is a push or a pull that acting on an object that changes the motion of the object, okay? This part right here, super important because we all know what the definition, that's a definition, and it's the definition of acceleration. Okay? All right, so a force is a push or pull acting on an object that can cause an acceleration. Okay, doesn't mean it does cause an acceleration, that it can. Think about the fact that if you're leaning on a wall, all right, you are pushing on it, but you're not necessarily causing a change in motion. So a force is a push or pull acting on an object that can change the motion, that can cause an acceleration. All right, basics for this one. So the unit for force is a Newton, and if you all kind of think back to when you first learned about forces, force is equal to mass times acceleration. Mass is a kilogram. Acceleration is meters per second squared, so therefore a Newton is a kilogram meter per second squared. Basically, we define it as the amount of force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. So kilogram meters per second squared. There are two types of forces. You got contact forces and field forces. Let's talk about field forces first. We're only going to refer to one of them right now, and that's gravity. A field force means that you don't have to touch it. For example, if you jump off of a table, you're not feeling the earth for that brief second. You're just being pulled down. So that's a field force. Another example of that for the electromagnetic would be if you ever go to the park and you know those slides are all plastic now because it's safer and they don't get quite so searingly hot. But you do the thing where you go over to the slide and you kind of you put your arm right over. You can't see it, but my arm's right over my keyboard. But as you put your arm in it, you're not touching anything, but you can feel your arm starts feeling funky, and if it's kind of close, the hair on your arms kind of stands up. That's a field force, an electromagnetic field force. The only one that we're going to deal with in this unit is gravity. The other three, those are coming into play: electromagnetic, weak nuclear, and strong nuclear. We're going to talk about those when we talk about universal gravitation. So we need to know this one right here. And we're going to need to know our contact forces. Contact forces all from different objects that have to be touching. So we've got friction, normal force, all right, applied force, tension, and a spring. Let's see what those definitions are. So friction is opposite motion, sliding, rolling fluid. Basically, if you are pushing it this way, friction acts opposite. If you are falling down because of the force of gravity, air resistance is pushing you up. The normal force has to have a surface, okay? All right, this is a typo, okay? Contact force means that there has to be a surface, okay? All right, if you're flat on something, all right, weight pulls you down, the force of gravity pulls you down, but the surface pushes you up. That's a normal force. You have to have a surface. Friction is also a surface. I can't spell. Okay, we say that friction, if you notice this diagram right here, is parallel. A normal force is always going to be perpendicular. I could be leaning on a wall. There I am. I'm a nice square. I'm leaning on a wall. And so I apply a force this way, and the normal force holds me out. If I'm on a ramp, okay, where's my normal force? Here's my surface. There's my normal force. It's from the surface. Applied force, that's just an F. It's something that's doesn't have one of these other labels. and it comes from another person or another object. So if it's touching it, we're good. Weight, lowercase w, is what we also call the force of gravity. And oh, that came out funky, didn't it? All right. So it's the force of gravity equals mass times the acceleration due to gravity. So it's mag, or we might say it's mg. The last one I'm going to mention right now is tension. And tension is the force along a string. So your stereotypical tug of war. All right, so if this guy's pushing this way and this guy's pushing this way, the force here is equal to the force there because it's tension, and the tension is the same all the way. But here's a question for you to think about, maybe find an answer to. If the tension is the same everywhere, that means that this person over here on, wrong button, this person over here on the right is pulling with the same amount of force as the person over here. How does somebody win a tug of war if they're pulling with the same amount of force? All right, we're going to figure that one out as we work our way through kind of Newton's second and third laws. All right, so those are our types of forces. We've got this is our only field force. All of our others are called contact forces. Now let's talk about something called net force. Okay, so net force is when you have a lot of different forces acting on an object. The net force is what's left after you add them all together. And we've been used to doing this, like when we add up different vectors going different ways, because force is a vector. Net force is called the resultant force. And let me see, the only other thing I want to add to that is sometimes you will see me write it like this. All right, math class. This means this is sigma, Greek letter, and basically might also see it as F net. Some people might write it as F total. Okay. All right, so that's a net force. Here's a simple example. This is what we call a balance force. So if the forces equal up and they're opposite, they cancel out. So 10 newtons east plus a negative 10 newtons west gives us a net force of 0. Unbalanced is when you have forces going different directions that they don't cancel out. All right. Now, unbalanced, this is important. Those are the ones that cause a change in the motion of an acceleration, i.e., they can cause an acceleration. So if it's unbalanced, there's no change in motion. That's going to go off the page. Can cause an acceleration. Balanced does not cause an acceleration. So unbalanced can cause. Balance does not. So let's say you've got 30 newtons east and you've got that same 10 newtons west. What's the net force? 20 newtons east. Now, let's go back to that idea of balanced forces, because balanced forces is equilibrium, okay? It's another way of saying balanced forces, that if all of our forces are balanced, it's sub to be in equilibrium. And there's two ways that you can have equilibrium, two ways to be balanced. So first off, your net force is 0 and your acceleration is 0. How do you get a net force of 0? All right, you get a net force when your velocity is 0 or your velocity is constant. Because if it's not one of these two things, it's accelerating, it's speeding up, slowing down, or changing direction. So if it's constant or 0, there's no change in motion. Now, free body diagrams. Free body diagrams, this is how we show the relative magnitude and direction of all of our forces that are acting on an object. We just draw the box and we draw them out. If you look at this one, these two are about the same line, so it's balanced in the y direction. These two are the same line, so they're balanced in the x direction. So we'll talk about different examples to see how to draw these, okay? So how do you draw a free body diagram? There's a couple of things in there. The basic steps are that you draw the object as a square, and all the forces are drawn as arrows going out of the square, okay? All right, they always come out like this. All right, this is no. This is yes. So when you're going through drawing a free body diagram, you're going to be given a scenario. All things that touch that object will have a contact force. So if it's something's touching it, there's a force, one of those 5 forces that we had up there. And anything that's on Earth will have the one field force that we're dealing with right now, which is the force of gravity. So all things that touch the object will have a contact force, okay? Don't forget, in our field force is our force of gravity. Let's do a couple of examples. Give me 1 second. Okay, so let's do a couple of examples. So let's say we've got a book on a table. Okay, so here's our table. I don't know why it's got a little bit of lag on it. And here's our book. So if we're going to sit here thinking about what are all of our forces on a book, well, we draw our object and we draw all the forces that are acting out of it. First, it's on Earth. So I'm going to draw my force of gravity. And it's not moving left or right. There's no forces that way, so I don't have anything there. But if you look at this picture right here, it doesn't look balanced yet, does it? Because if it was just that, it would be falling, which means there has to be another force balancing it. And that other force is the force from the table up. That is our normal force. So there's example 1. Okay, so this is one example. This is balanced. Okay. So it says velocity equals 0. Oh, I don't know what I just did there, but I did something. Okay, let's do another one. Let's say a skydiver. Okay, so here we go. Ooh, and he's going down. So if he's a skydiver, here's our skydiver. And, well, in an absence and simple flight cast, so no air resistance. No air resistance. So what's it going to look like? That's it. So what is he doing? He is accelerating downwards. And yes, I wrote F weight. You can also write F of G. Honestly, it doesn't matter too much. Just be consistent. Okay. Now let's talk about what if there was air resistance. Okay, so here's 2. Okay, so 2A. So 2B will be with air resistance. So with air resistance, we still got the skydiver, right? But now there's air resistance. So he's still falling, he's still accelerating, he's not moving at a constant velocity. So we would have air resistance, but it wouldn't be nearly as big as the one going down. Okay, so this is now an unbalanced scenario. All right, let's try another scenario. So next one. Here's 3. Let's say we are pushing that same book we had earlier. We're going to push a book across the table. Okay. And so we're going to, I can't draw, guys. There's our hand, and it's pushing that book. So what are our forces that are acting on it? Well, here's our book. It's on Earth, so there's always a weight force, force of gravity. I started that way, I should finish that way. It's on a table and it's not moving to the left, not moving up or down, which means we have a normal force, and that should be balanced. And we have an applied force. It's going this way. Now, if this was a scenario, this would not be balanced, okay? But let's say we put in here pushing a book across the table at a constant speed. If it's pushing across the table at a constant speed, what we have here cannot be it. We have to have something in here that's going to make it balanced. So we would have to have, that indicates that there must be friction. And friction should be the same, approximately the same length. Now this is balanced. And I don't know what happened with that. I have to figure out how I do that sometimes. Something I'm not quite that used to. So it's balanced and moving at a constant velocity. We're going to call that good. So that covers, we just talked about types of forces, net forces and equilibrium. We talked about free body diagrams. There's one more topic you're going to cover, and that is a video link that I'm going to put up on mass and gravity from conceptual physics. It's pretty good, and pay attention to especially the demonstration. So it's going to be, dang, it's being weird. All right, it's going to be Hewitt-Druitt, and I'll put the link up. I know it's silly, but still, it rhymes. Mass and weight. I'll get both of those up. Get that up for you. It's about another 6 minutes. So anyway, have a good day. Talk to you later.